Hi guys, I'm Monica. I welcome you all to my channel Aerokar. Proceeding further in our journey of aerodynamics, we will discuss about boundary layer and its effects. In our previous video, we had ended on the topic or on the word boundary layer, which is a thin viscous layer found around the airfoil, which is adjacent to the body, and we had named that as boundary layer. So now, how is this boundary layer important and what effects it has on the flow surrounding any object? Let us have a look. Without any further delay, let's get started. Now, before we dive into the actual topic, what we are going to discuss about the boundary layers, let us have a question segment which covers partial topic. And the first question is that what effect does the thin boundary layer has on the flow? Now, in the previous video, as we saw that the boundary layer is a very thin segment which is around the airfoil, a thin layer of viscous flow which is around the airfoil. Now, when this layer is pretty much thin enough, what kind of effect this must be having on the flow, and why should we give so much importance to this? Let us see. Now, the first thing is that it is a source of friction drag. Because of this viscous flow in the boundary layer, there is a friction drag over the aerodynamic body. What is the term drag? Some people might be knowing it and some people might not be aware of it. So drag is the force which is opposite to lift. So for an aircraft, if lift is the force which takes an aircraft up, drag is the force which is dragging it behind. In simple terms, we just call drag as a force which is resisting an aircraft to fly. That is, it tries to pull the aircraft a little behind. So because of this viscous flow, there is a small contribution in the drag force of the aircraft. That is, there is a formation of friction drag. Now, there is a term called pressure drag that I have written over here. What is this pressure drag and how it is formed, or what exactly is happening? Now, what happens is, around this airfoil, when there is a boundary layer, as the flow comes behind, that is at the trailing edge, at the end point of the airfoil, we see that the flow is no more sticked to the airfoil. As we see in streamlines, we see that the flow is sticked to the airfoil and following a particular streamlined pattern. But when there is a boundary layer and the presence of viscous flow in the boundary layer, what happens is there is a flow separation observed. And due to this flow separation, when the flow is separating from the surface, what happens is there is a change in pressure distribution. Previously, the pressure distribution in a streamlined flow and in a viscous flow in the presence of boundary layer is different. So when there is a change in pressure distribution on the surface, it results in increase of drag. Due to this change of pressure distribution, there is an increment in drag, and we call that term as pressure drag. Now we saw how this thin boundary layer, which seems to be really thin, and what a huge contribution it is giving to us in the flow in our aerodynamic study. Now, the second thing comes, we had discussed a point on velocity gradients, that the velocity gradients are large inside the boundary layer. So now, how are these velocity gradients large? Why are these velocity gradients becoming large when there is a boundary layer? Let us have a look. Let us consider an airfoil, As in our previous video, we had considered the same example, and here also we are going to take the same one, that is an airfoil. Now, initially what we are going to do is, we are going to consider an purely inviscid flow over here. Okay, in an airfoil, we are going to consider an purely inviscid flow. Now, by definition, we all know that what is an inviscid flow? Inviscid flow is where we do not see any effect of friction, right? This is the definition. And so we can see here that if it is on the surface of the airfoil, I can see my velocity is VB, because there is no effect of friction over here. But in reality, what is happening is this velocity VB at the surface, is it actually VB at the surface of the airfoil? No, that is not VB. There is something which is happening different in reality when we observe the real flow over an airfoil. When there is a presence of boundary layer, there is something different that is happening. Now, what happens is, due to that friction between the molecules, the thin layer of molecules which are immediately adjacent to the surface of this airfoil, the molecules which are immediately adjacent to the surface of this airfoil, they stick to the surface of the airfoil because of friction. Okay. So now if they are sticking to the surface of the airfoil, which means at this point on the surface of the airfoil, my velocity will be 0, right? So this is what is happening in reality, which is not being considered in the inviscid flows. And this condition where, because of the friction of the molecules, they are sticking to the surface and the velocity is 0, this condition is known as no slip condition. That is, molecules are sticking to the surface of the airfoil and they are not slipping away. That is why we call it as a no slip condition. And this no slip condition is the cause of large velocity gradients. Large velocity gradients. Now, question arises, we have discussed that in reality what is happening is, because of the no slip condition and because of the molecules sticking to the surface, the velocity is 0 over there, and this is due to the presence of boundary layer, and this is the reason why I am having large velocity gradients. Now, how is this rise in velocity gradient actually happening in the boundary layer? If you remember my first video, we had discussed that whenever we are studying, it should be like what, why and where, correct? Now, there is one more addition to this. Whenever we are studying any topic which is specially related to physics, we need to know what is the physics behind it. If this is happening, why it is happening, and also we need to know how it is happening, right? So the next question we ask ourselves is, how is this happening? Let us have a look. Let us have a look at a magnified view of boundary layer. This was an airfoil where we considered an inviscid flow. Now we'll have a look at magnified view of boundary layer. This is my airfoil, and over here the dotted line that you can see is the outer edge of boundary layer, and this is my boundary layer. Okay, so this is a magnified view that we are looking at. We'll consider 2 points along the y-axis, point A, which is on the surface of the airfoil, and point B, which is on the outer edge of my boundary layer. As we discussed, on the point over here, that is on the surface of the airfoil, my velocity will be 0, and this is due to no slip condition. Because of the no slip condition in the molecules, I have velocity at point A as 0. Now, if I move ahead in y direction, by the time I reach point B, which is the outer edge of the boundary layer, I see that there is a finite value of velocity. When I calculate, I get a finite value of velocity, and let us name that finite value of velocity as VB, which is at the outer edge of the boundary layer. Now, on the contrary, here you need to see or remember that there is a point when we consider inviscid flow, this VA is neglected over here and VA is equal to VB. That is, this which is at the outer edge of the boundary layer is considered on the surface of the airfoil, because in inviscid flow we assume that there is no friction. Coming back to our boundary layer concept, here you see VA is equal to 0 and we have a finite value VB over here. Okay. So what we are seeing over here, over a thin, that is, as we said, this boundary layer is very thin, and as you can see, it is a very short distance from A to B. So within this short distance from 0 to a finite value, so for a thin region, there is an increment in the velocity gradient, which is large. So that is the reason we see how it is happening, that is increase in the velocity gradient. Now, main factor over here, what is acting is your shear stress. Tau W over here is your shear stress at the wall. So we can reach a conclusion that boundary layer is a segment where frictional effects are more dominant. That is, the frictional effects between the molecules are more dominant in the boundary layer. This was all about the 3 questions, that how the boundary layer is having an effect on the flow. Let us have a look at the concept called velocity profile and temperature profile. Now, these are something new terms which we encounter in boundary layer or with respect to boundary layer: velocity profile and temperature profile. So here what we are doing is, let us consider a surface over here. This is a surface that I am considering, and this is my outer edge of the boundary layer. Now, at surface, as we saw, velocity will be 0, correct? And this is due to the no slip condition. So, as we see that there is a continuous increase in velocity in y direction. This is our x direction and this is our y direction. So, as I move along y-axis, I see that there is an increase in velocity taking place, and by the time we reach the outer edge of the boundary layer. Okay. So now if I say the definition of velocity profile, what exactly a velocity profile gives is, it gives the variation of velocity inside the boundary layer as a function of y. So along the y-axis, we see the variation of velocity. So velocity profile is something which gives me the variation of velocity as a function of y. Now, here I am seeing that we are getting one shape of a velocity profile. Question arises that will I have the same velocity profile, the same variation curve, the curve that you are observing, this curve. The curve that you're observing over here, will it be same at every point? Like, let us say this is my point 1. Here is my point 2. At point 3, we already have a velocity profile, and this is my point 4. So, let us say that I want to sketch my velocity profile, that is variation of velocity at all these 4 points. Now, the point over here is, at every point I will have a different velocity profile. Okay. So this was about the velocity profile. Proceeding further, we will have a look at temperature profile. Now, is it that only velocity is varying along the boundary layer or inside the boundary layer? No. We also see that there is a variation in temperature from the surface to the outer edge of the boundary layer. Similarly, as in velocity profile, we consider a surface over here. And let us say my x-axis is tangent to the surface and normal to the y-axis is normal to the surface, that is x is parallel. Okay. Now, if I see now, when you compare your velocity profile to the temperature profile, it has a quite different curve going ahead, right? Now, what exactly is happening in this boundary layer that there is a rise in temperature or variation in temperature for that matter? So the first thing, the gas temperature at the wall, that is at the surface, it is the same, the no slip condition. Let us consider. So let us say that TW is my temperature at the wall, which means it will have some certain value. It is not possible to be 0. So it will have its own initial temperature at the wall. Okay. Now, why is this temperature rising? So there are two reasons that there is a change in temperature inside a boundary layer, and those two reasons or two mechanisms are thermal conduction and frictional dissipation. So these are the two mechanisms due to which we see a change in temperature inside the boundary layer. So all of you keep this in mind. These are the two important terms which you need to keep in mind: thermal conduction and frictional dissipation. Now, what is thermal conduction? Thermal conduction is something where heat is transferring from a hotter region to a colder region due to random movement of molecules. As of now, let us have this simple definition about thermal conduction. Okay. Frictional dissipation. Frictional dissipation, if in simple terms, if we want to understand, it is just the heating of gas when one streamline rubs against each other. When the two streamlines are rubbing against each other and there is friction happening between them, then we see this frictional dissipation. Now, if we want to have a more clearer look or a more deeper look into this frictional dissipation, what happens is, as long as a fluid element is moving along a streamline inside the boundary layer, for example, let us consider we have a fluid element over here, okay, and there is a fluid element inside a boundary layer. So it is moving with its own pace in x direction. What happens is the speed or the velocity of this fluid element comes down or decreases due to frictional shear stress. So there is a decrease in velocity of the fluid element because of frictional shear stress acting on it. Okay. Now, I bring this fluid element inside. Let us say that the fluid element which was outside the boundary layer, due to movement of flow, interaction of flow, this fluid element is coming inside the boundary layer. Now, when this fluid element is coming inside the boundary layer, first thing what is happening is there is a decrease in velocity because of frictional shear stress. The second reason that is happening is it has its own kinetic energy. When it is entering inside the boundary layer, it has its own kinetic energy which is converted into internal energy when it comes inside the boundary layer. And this conversion of kinetic energy into internal energy results in the increasing gas temperature inside the boundary layer. So here we had considered just one fluid element, but in reality what happens is there are many such fluid elements which are coming and going outside. So there are many such fluid elements which are interacting outside and inside the boundary layer. So because of that, when that kinetic energy is converted into internal energy, there is a rise in gas temperature. Now, if we talk about the definition of temperature profile, it is similar to the velocity profile. It gives the variation of temperature as a function of y. Proceeding further, we will introduce some new terms. Now, the slope of velocity profile is one of the most important term at the wall. Basically, at the wall of any surface, this whatever is the slope of velocity profile, it is of prime importance. The reason being, it governs the wall shear stress, which is denoted by tau. Now, let us consider dv by dy, that is your velocity gradient. dv by dy is your velocity gradient, and y is equal to 0. That is on the wall, y will be equal to 0. Okay, so this is my velocity gradient at the wall. Okay, so if I want to write shear stress at the wall, this is how I'm going to write my shear stress or denote shear stress mathematically. Okay, as discussed previously, mu is my absolute viscosity coefficient. Mu is absolute viscosity coefficient, or you can just call it as viscosity. Now, in our previous video, there was a sentence where I told that we are taking mu as a constant of proportionality when we were talking about streamlines, correct? But we also discussed a statement, even though it is called as constant of proportionality, but it is not constant in all the cases. Mu is varying, right? So when we look at the term mu, that is viscosity, it is different for gases and liquids. Now, if we see how viscosity is varying with respect to temperature, if I have a look at that, let us have a look at the graph. If, for example, I am looking for air, let us consider air initially. On my y-axis, I have viscosity and this is temperature. So if I sketch the simple variation, if I just want to have a look, so this is how I'm going to have a look. That is, there is a linear variation for air as there is an increase in temperature. So therefore, for gases, when there is a rise in temperature, it results in rise in viscosity, whereas it is vice versa for the liquids. For liquids, if there is a rise in temperature, there is a decrease in viscosity. What happens is, as the temperature rises, air gets thicker, so which means there is a rise in viscosity. Now, if we talk about the units of viscosity are kg per meter second. Now, this was about the slope of velocity profile. Now, what is the task of temperature profile, or what is the importance of slope of temperature profile? Slope of temperature also has its contribution, and it dictates the aerodynamic heating. Aerodynamic heating to or from the wall. Aerodynamic heating, a new term into our journey of aerodynamics. What is aerodynamic heating? Let us have a look. Before we understand what aerodynamic heating is, what if I consider a temperature gradient dt by dy and I say y equal to 0, which means this is my temperature gradient at the wall, right? If I want to write aerodynamic heating rate at the wall, that is, aerodynamic heating rate means energy per second per unit area. So that can be mathematically written as Q dot W, which is equal to minus K multiplied by the temperature gradient at the wall. We see a new term over here, K. This K is thermal conductivity. This K is your thermal conductivity. What does this negative sign indicate over here? So this negative sign denotes that heat is conducted from a warm region to a cooler region in the opposite direction from the temperature gradient. Now, what exactly does this statement mean? Let us have a look. For example, if my temperature gradient is positive, okay, what is happening if my temperature gradient is positive? The heat is transferring from the gas into the wall. Having a clear look with the diagram over here, if I have this as my temperature profile and this is the gas over here. So if I say that my temperature gradient, this temperature gradient is positive, what is happening? The heat is transferring from this gas into the wall, which is opposite to the direction of increase in temperature. So my temperature is increasing in this direction and heat is transferring in this direction, right? Now, what happens if my temperature gradient is negative? Then there is a temperature decrease in the direction above the wall, that is in this direction above the wall, but there is a decrease in temperature. The heat transfer is taking place away from the wall into the gas. Now it is again in opposite to the direction of temperature increase, because now if temperature is decreasing in this direction and positive y direction, which means my temperature increase will be in the opposite direction, that is negative y direction. Okay, so by this equation we see that heat transfer between the gas and the wall is taking through a phenomenon called as thermal conduction. The heat transfer that is taking place between this gas and the wall, that term, the heat transfer that is taking place, is known as aerodynamic heating. Now, where do we observe this term aerodynamics, or where it is most importantly considered? So basically, this term aerodynamic heating is most importantly considered in supersonic flows. It is a very, very important term in supersonic flows. And if you look at hypersonic flows, then aerodynamic heating is the term which is dominant in hypersonic flows. And if you see K relating it to viscosity, then it is a physical property of fluid, right? Thermal conductivity is a physical property of fluid, and it is a function of temperature. So I can say that thermal conductivity is directly proportional to viscosity. This is the relation between thermal conductivity and viscosity. So on this note, we end the discussion of boundary layer and its effects on the flows. Further in the upcoming video, we will be discussing more new terms with respect to boundary layer. Thank you for listening. Stay tuned.